Can you believe a laser, thinner than a human hair, is racing through the air to deliver your Netflix movie at lightning speed? No wires involved, just pure light? So here's the uncomfortable question. If light is so powerful, why does fiber still lose signal? If you already understand what optical fiber actually is, why we abandoned copper, and why light, not electricity, became the hero of modern networks, then this video is the next unavoidable step. If you haven't seen those foundational videos yet, head over to the Raahi online homepage to catch up. Because today, we're not talking about how fiber works. We're talking about where it quietly starts failing. Remember how we said light stays trapped inside the fiber? That magic happens because of the core and cladding relationship. Total internal reflection, perfect angles, perfect physics. But here is what most people don't realize. That perfect reflection only works under ideal conditions. The moment reality interferes, loss begins. This is what engineers call fiber transmission loss. Not a break, not a fault, just light slowly losing strength as it travels. This happens because of absorption and scattering, where the glass itself or tiny impurities soak up or deflect the light. Imagine light hitting a microscopic grain of dust inside the glass. It doesn't just stop, it shatters in 1,000 directions. That's Rayleigh scattering. It's the same reason the sky is blue, but inside a fiber, it's an engineer's nightmare. Or imagine the glass itself acting like a sponge for specific wavelengths of light. That's absorption. Even the purest glass has water peaks, residual hydroxyl ions that soak up light at specific frequencies like a black hole. If you've already studied how data travels as light, you know that signal power is everything. Less power, less margin. Less margin, unstable network. That's why attenuation isn't theory. It's a design constraint. Think back to when we talked about the fiber jacket. It looks tough, feels strong. But the glass inside, extremely sensitive. One tight bend behind a rack, one sharp turn inside a closure, and suddenly the light that should stay inside the core starts escaping. This is macro bending loss, where the angle of reflection becomes too sharp for the light to stay trapped. Think of it like a high-speed car trying to take a hairpin turn at 200 miles per hour. It's going to fly off the track. In fiber, that track is the core, and the car is your data. But there's also microbending, microscopic imperfections or pressure on the fiber that cause tiny, invisible leaks along the entire length of the cable. No alarms, no sparks. Just a weaker signal. You've already seen real-world fiber connectors, tiny, precise, unforgiving. Now here's the twist. A connector can be perfectly installed and still destroy your signal. Why? Because light doesn't tolerate dirt. One microscopic dust particle can block the core that you learned is only microns wide. That's not exaggeration. That's physics. Earlier we explored why fiber is future-proof. Now let's test that claim. Under the ocean, signals travel thousands of kilometers. No maintenance crews, no reboots. Yet engineers still expect signal loss. That's why optical amplifiers exist. Because even the best fiber, using the best wavelengths, still obeys the same rules you're learning now. This is where everything connects: bandwidth, power, distance, loss. Professionals don't hope fiber will work. They calculate. Every splice, every connector, every meter of fiber is already accounted for before the cable is even installed. This is the mindset shift from learner to engineer. Here is the truth most channels want to tell you. If you don't fully understand how fiber works, why light was chosen, core versus cladding, single mode versus multimode, and bandwidth fundamentals, then concepts like attenuation, power budget, and dBm will always feel confusing. Not because they're hard, but because they're connected. Fiber knowledge is not chapters, it's a chain. Miss one link, and the rest feels blurry. If you're serious about mastering optical fiber, not just memorizing terms, then make sure you understand the foundation this video is built on. Check out our previous videos on the homepage to complete your knowledge. Because everything we discuss next on this channel depends on it. Raahi Online is building that chain, one link at a time. Imagine a world where every byte of data you send, every video call, every transaction, is a pulse of light. But that light is under constant attack. From the very glass it travels through to the dust in the air, the journey is a battle against physics. We've covered the basics of how light stays in the core, but now we're diving into the why behind the failures. If you missed our deep dive into single mode versus multi-mode, you're missing a huge piece of the puzzle. Go back to the Raahi online homepage and watch that first. It's the only way to truly grasp why some fibers lose signal faster than others. We're not just learning terms, we're building an engineering mindset. Every decibel lost is a challenge to be solved. Every connector is a potential point of failure. This is the reality of high-speed networking. Stay with us as we break down the optical budget, the ultimate tool for any fiber professional. This isn't just theory, it's the blueprint for the future of communication. Join the Raahi online community and let's master this technology together, one link at a time. Let's look at a real-world scenario. A data center in Singapore communicating with one in New York. Thousands of miles of fiber, hundreds of splices, and dozens of connectors. A tiny smudge from a technician's finger can lead to each connector losing 0.5 decibels, which could ruin the whole link. That's why we emphasize cleanliness and precision. It's not just about the big cables, it's about the microscopic details. We'll be exploring how to calculate these losses in our upcoming optical link budget masterclass. But before you get there, you must have the basics down. The core, the cladding, the refractive index. These aren't just words. They are the laws of the game. If you're feeling a bit lost, that's a sign you need to revisit our Raahi online homepage. Don't skip the foundation or the house will fall. We're here to make sure you build it right. Think about the Fresnel reflection, the loss that occurs every time light passes between two different materials, like glass and air. Even a perfectly clean connector has this. Now multiply that by every connection in a citywide network. You start to see why engineering isn't about perfection, it's about managing imperfection. We're going to show you exactly how to measure these losses using an OTDR, an optical time domain reflectometer. But to understand the OTDR's graph, you need to understand everything we've discussed today. The journey from a student to a professional starts here, by respecting the physics and mastering the chain of knowledge. Raahi Online is your partner in this journey. Let's keep building.